Greetings, this is Professor Roman. Let's continue our lectures on linear algebra. We've been studying eigenvalues and eigenvectors. We did so in the last lecture. Now it's time to consider the problem of actually finding the eigenvalues of a linear operator. Unfortunately, this problem doesn't have an entirely satisfactory solution, as we'll see. Since the eigenvalues of a linear operator are the same as the eigenvalues of any matrix representation of the operator, we can concentrate on the problem of finding the eigenvalues of matrices. This will apply, of course, to the finite dimensional case. By definition, a scalar lambda in the base field of a matrix A is an eigenvalue if and only if there's a non-zero vector V for which this equation, the eigenvalue equation, holds. But this is equivalent to saying that this matrix, lambda I minus A, is singular, non-invertible. And another way to say that is that the determinant of this matrix is 0. So this prompts a definition. The characteristic polynomial of a matrix A, and this should be an n by n matrix, I have to fix that, is the polynomial determinant of xi minus a. X here is an independent variable. I'm going to use the notation c sub a of x for the characteristic polynomial. I think there's a variety of notations, but this one seems reasonable. So the characteristic polynomial of a matrix A, an n by n matrix, is determinant xi minus a. I, of course, is the identity matrix of size n by n. The characteristic equation of the matrix A is just found by setting the characteristic polynomial equal to 0. It's worth mentioning that some authors, many authors, define the characteristic polynomial as the determinant of the matrix A minus xi rather than xi minus a. So it's the negative of what we have used in our definition. So the two characteristic polynomials are the same up to algebraic sign, and so that has no effect on the solution set of the characteristic equation, which is the important issue here. Determinant xi minus a equals 0 and determinant a minus xi equals 0 have the same solutions, including multiplicity. Since the characteristic polynomial of a matrix is just a determinant, and it's computed from the entries of this matrix xi minus a using only the 4 basic arithmetic operations, addition, subtraction, multiplication, and division. The characteristic polynomial is in fact a polynomial over the smallest field that contains the entries of the matrix. So, for example, if A has only rational entries, then xi minus a has only rational entries, or actually the entries are polynomials with rational coefficients. then when we take the determinant, we're going to get a polynomial over the rational field. So regardless of how we think of the matrix A, we may think of it as a real matrix or a complex matrix. Its characteristic polynomial still has entries over the rational field only. So I'm going to refer to this as base field independence. It doesn't matter what you decide to use as the base field of a matrix. If you have a matrix with rational coefficients, rational entries, you can say the base field is the rational field or the real field or the complex field. It doesn't change the matrix. The characteristic polynomial is a polynomial with rational coefficients. So, the characteristic polynomial of a matrix has coefficients in the smallest field containing the entries of the matrix, and so is base field independent. This will be important because, as I mentioned before, there are times in particular when we want to think of a real matrix as a complex matrix because the complex field is algebraically closed, whereas the real field is not. And we now know that regardless of whether we think of a real matrix as a real or a complex matrix, it's not going to affect the characteristic polynomial. One of the consequences of this fact is that the spectrum of a matrix, which, as we will see, are the roots of the characteristic polynomial that lie in the base field, will depend on the choice of base field, even though the characteristic polynomial does not. So, for example, or to put it more plainly, you have a matrix A. Let's say it has rational entries. You can think of A as a rational matrix, a real matrix, or a complex matrix. The characteristic polynomial does not change, but the roots of the characteristic polynomial may be different if you allow only rational roots, if you allow real roots, or if you allow complex roots. The solution set may expand. And so, for example, if the characteristic polynomial is x squared plus 1, as a real matrix there are no roots, and therefore there are no eigenvalues, but as a complex matrix, same characteristic polynomial, x squared plus 1, but now there are two roots, and therefore two eigenvalues. Okay. So, I'm going to make the following definition. Let A be an n by n matrix over a field F, and let K be any field containing the entries of A. The K spectrum of A is the set of all roots of the characteristic polynomial of A that lie in K. And this is the symbology. So for each field, let's say qualifying field, in other words, field that contains the entries of A, that is a candidate for base field. You can simply declare this is a matrix over K. And therefore, it has a spectrum as a matrix over K. It has eigenvalues that are elements of the base field K. And those eigenvalues are, in fact, the roots of the characteristic polynomial that lie in the field K. Examples. The characteristic polynomial of the real matrix A is this, x squared plus 1. I could have said this was a rational matrix, same characteristic polynomial. Could have said it's a complex matrix, same characteristic polynomial. As a real matrix, this has no roots because its only roots are the two non-real roots. So the real spectrum of A is empty, but the complex spectrum consists of these two eigenvalues. The rational spectrum is empty as well. Another example, this real matrix has this characteristic polynomial, and these are its solutions. These are real eigenvalues. So as a real matrix, these are its eigenvalues. To get the corresponding eigenvectors, we have to solve a system or some systems of linear equations. For example, to compute the eigenvectors associated to the eigenvalue lambda 1, take the plus sign there, then the eigenvalue equation looks like this, and the solution looks like this. So this is the eigenspace generated by this single vector. It's a one-dimensional eigenspace. This matrix has this characteristic polynomial. I don't need to even say what the base field is just to compute the characteristic polynomial. If you look at the factorization here, this is over the complex field. The real spectrum of A just consists of the single eigenvalue 1. It's the only real root of the characteristic polynomial. The complex spectrum consists of these three roots of the characteristic polynomial. Okay? If you have two similar matrices, A and B, that means there's an invertible matrix P for which B equals P inverse AP, and so xi minus B is equal to P inverse xi minus AP. In other words, xi minus A and xi minus B are also similar. Taking determinants shows that the characteristic polynomial of B is equal to the characteristic polynomial of A. So the characteristic polynomial is yet another similarity invariant. Similar matrices have the same characteristic polynomial. That allows us to define the characteristic polynomial of a linear operator on a finite dimensional vector space to be the characteristic polynomial of any of its matrix representations. Okay. I'm just looking back here to see if I should have said that this whole discussion concerns finite dimensional vector spaces. Once if we want to take the characteristic polynomial, we have to have finite dimensional vector space. So the characteristic polynomial of a matrix is an invariant under similarity. Similar matrices have the same characteristic polynomial. But unfortunately, this is not a complete invariant. There are matrices with the same characteristic polynomial that are not similar, and I'll show you an example momentarily. The spectrum of a linear operator is the set of roots of the characteristic polynomial of the operator that belong to the base field. And every complex linear operator has at least one eigenvalue, and that's because the complex field is algebraically closed, and so every non-constant polynomial over the complex field has at least one root. Here's the example I mentioned. I was going to show you. These two matrices have the same characteristic polynomial, but they are not similar, and I'm going to leave that for you to check. Well, now we come to, I guess you might say, the bad news and the good news with respect to finding eigenvalues for matrices, let's say. We know now that the eigenvalues of a matrix are the roots of the characteristic polynomial that lie in the base field. But this is a polynomial equation whose degree is equal to the size of the matrix. Say, call it n. Well, if n is bigger than or equal to 5, if our matrix has size 5 by 5 or bigger, there is no general algebraic formula similar to the quadratic formula, the cubic formula, or the quartic formula. Nor can there ever be a general formula for the solutions to the characteristic equation when the size is 5 by 5 or bigger. This is a subject that comes when you study this, when you study field theory, Galois theory. The culmination of elementary field theory is in the Galois theory, the theorem that says that there cannot be a general algebraic formula that uses only the 4 basic arithmetic operations and the taking of nth roots that will give solutions to all quintic or higher polynomial equations. Okay. So, in short, the bad news is that in general, we cannot solve the characteristic equation to get the eigenvalues of a matrix. We can do so for quadratic, for 2 by 2 matrices, even the cubic and quartic formulas are kind of a disaster. They're very complicated, and one doesn't use them very often. I've never had occasion to use one. So it's doable but not easy for 3 by 3 and 4 by 4 matrices, doable and easy for 2 by 2 matrices. For 5 by 5 matrices and bigger, it's not doable at all. I mean, you may encounter some matrices where the characteristic equation is easy to solve, even if it's a higher degree. But in general, we don't have a formula. Fortunately, there is some good news from a practical perspective, from the perspective of applications of this subject to applied math, to physics, to chemistry, to whatever. An exact solution to the characteristic equation is often less desirable than an approximate solution. After all, in applications, you are likely to be computing with the eigenvalues, and you may be using a computer to do that. It's going to truncate your eigenvalue anyway if it doesn't fit naturally into the computer, so you're going to end up with an error. If, for example, a solution to the characteristic equation looked like this, that wouldn't be of immediate practical use. If you approximate it sufficiently, you might get something like this, which might be much more useful when it comes to computation with the eigenvalues. So, the art of approximating the eigenvalues of a matrix is a very important area of applied linear algebra. That's a bit outside the scope of the present lecture series. So I'm not going to pursue the matter of approximating eigenvalues, except for some exercises in my book concerning Gershgorin disks in the complex plane, which provide one method of approximating the values of eigenvalues. Of course, there are other methods. For example, here's a real matrix 3 by 3. Here's the characteristic polynomial. One could use the cubic equation, cubic formula, to get the exact roots of this polynomial. I haven't done that. I have a feeling they don't look very pleasing. But Newton's method for approximating the solutions to this equation, or in other words, the eigenvalues, will give these three values. And as I said before, this may be much more useful in actual computation, even though there's an error here because these are just approximations. This should be an approximation sign. Okay. Despite the fact that there are practical limitations to the value of the characteristic equation, it has a great deal of theoretical value, as we will see as we proceed. Okay. Since invariant subspaces and reductions of an operator are important concepts in the study of the structure of an operator, we've discussed this already, we should examine the relationship between the characteristic polynomial of an operator and the characteristic polynomials of the restrictions of the operator to invariant subspaces. Remember, if we have an invariant subspace, we can restrict the operator to that subspace, and that gives us a legitimate operator on the subspace. It will have a characteristic polynomial as well. What is the relationship between the characteristic polynomial of the restricted operator and the characteristic polynomial of the full operator, the unrestricted operator? That's the question. And, as is often the case, beginning with a matrix point of view provides a little more transparency. So, as far as matrices are concerned, let's first consider a block upper triangular matrix. So this is block form. B1 through Bm are the block diagonals. The asterisk represents arbitrary unknown entries. Below the block diagonal are zeros. We discussed in chapter 0 the fact that the determinant of this matrix is the product of the determinants of the block diagonal, of the diagonal blocks. Okay. So this would apply to a matrix of the form xi minus a, and would tell us that the characteristic polynomial of the matrix A is the product of the characteristic polynomials of the matrices B sub I. So now suppose we have a linear operator and S is a tau invariant subspace of V. Then we can extend an order basis B for the invariant subspace to an order basis for the full space by tossing in more vectors B prime. And as we have seen back in chapter 2, the matrix of tau with respect to the full basis looks like this. This was the reason that invariant subspaces will lead to relatively simple matrix representations of a linear operator. This is a first step. We're getting a bunch of zeros down here, hopefully. That's a good thing. In any case, the characteristic polynomial of tau is the same as the characteristic polynomial of this matrix representation of tau, and what we have just discussed, this is the product of the characteristic polynomials of these two matrices on the block diagonal. So characteristic polynomial of tau is the characteristic polynomial of tau restricted to the invariant subspace times the characteristic polynomial of the matrix R. We don't know much about R at this point, but what we can say then is that the characteristic polynomial of the restriction of tau to S divides the characteristic polynomial of the unrestricted operator. There's not much we can say beyond that at this point, because the matrix R does not, in general, represent the restriction of tau to the complementary subspace generated by B prime. It's the asterisk here that gets in the way. If this should happen to be all zeros up here, we'll have a reduction. I'll get to that in a minute. But for now, if there's a non-zero entry up here in this area represented by the asterisk, then we can't say anything further. But it's still very important that the characteristic polynomial of the restriction divides the characteristic polynomial of the full operator. If we do have the good fortune to find an actual reduction of tau, and it doesn't have to be just in two invariant subspaces, but we can have an invariant direct sum like this, and if B sub k is an ordered basis for S sub k, for all k, we can stick those together and get a basis for the whole vector space. And the matrix of tau with respect to that basis is now block diagonal. And so the characteristic polynomial of tau is the product of the characteristic polynomials of the restrictions. So here it is in summary. We have a block upper triangular matrix. The characteristic polynomial of the matrix A is the product of the characteristic polynomials of the B sub i's. This is strictly matrix formulation. As far as operators are concerned, if we have a finite dimensional operator, linear operator, and if S is an invariant subspace, then the characteristic polynomial of the restriction will divide the characteristic polynomial of the operator. If we have a reduction of reduction of tau, then the characteristic polynomial of tau is the product of the characteristic polynomials of the restrictions. So here's an example. This matrix is block diagonal. If the basis B is V1 through V8, V1, V2, and V3, if you just restrict to V1, V2, V3, you get an invariant subspace S1. When you restrict to the subspace generated by V4 and V5, you'll get an invariant subspace S2, and finally for this one, then the characteristic polynomial of tau is the product of the characteristic polynomials of each of the restricted operators. And the restricted operators have these three matrix representations. So the characteristic polynomial of the first restriction, which I call tau 1, restricted to the subspace generated by V1, V2, and V3, this is the matrix representation, this upper block, this upper block. And so we take its characteristic polynomial, we get this cubic. We do the same for the other two blocks, multiply them all together, we get the characteristic polynomial of tau is this product. As I mentioned, I think in the last lecture, eigenvalues actually have two forms of multiplicity, one of which is the geometric multiplicity that we've already discussed. That's the dimension of the eigenspace for an eigenvalue. The other type of multiplicity relates to the eigenvalue as a root of the characteristic polynomial. So here are the definitions side by side. lambda is an eigenvalue of a linear operator. The geometric multiplicity is the dimension of the eigenspace. We denote it this way. The algebraic multiplicity of lambda, of an eigenvalue lambda, is the multiplicity of lambda as a root of the characteristic polynomial. And we'll denote the algebraic multiplicity this way. Now this applies only if the operator is finite dimensional, so it has a characteristic polynomial. So perhaps it's best to say that this is a finite dimensional linear operator. The geometric multiplicity doesn't require that, but the algebraic multiplicity does. But we're mostly interested in finite dimensional operators because they have matrix representations, so they're much easier to understand. There is an important relationship between these two multiplicities. And again, we need finite dimensional here. If tau is a finite dimensional linear operator, then the geometric multiplicity of any eigenvalue is less than or equal to its algebraic multiplicity. There is a term for an eigenvalue for which this inequality is strict, where the geometric multiplicity is less than, strictly less than the algebraic multiplicity. It's called a defective eigenvalue. That's not a term that you need to worry about too much for us, but I thought you should at least hear it. I'm going to give you two slightly different proofs. Perhaps the most elegant proof goes as follows. We can first we can extend an ordered basis B for the eigenspace E lambda to an ordered basis for the whole space V. So the geometric multiplicity of lambda is the size of the basis B, which I'll call K. And that's the geometric multiplicity. Now, since the eigenspace is tau invariant, we know that the operator can be restricted to the eigenspace, and the characteristic polynomial of the restriction divides the full characteristic polynomial. But what does the restricted operator look like? It's just multiplication by lambda. So its matrix representation is lambda times the identity of size k by k. This looks like this. And so its characteristic polynomial is just x minus lambda to the k. Remember, k is the geometric multiplicity of lambda. So we get this, and so the algebraic multiplicity, which is the multiplicity of lambda as a root of this characteristic polynomial, is at least as big as k. So the algebraic multiplicity is greater than or equal to k, the geometric multiplicity. And I think we can be a little more transparent in this proof as follows. Again, extend an ordered basis B for the eigenspace to a basis for the full space. And again, the size of B, k, which I'll denote by k, is the geometric multiplicity. The matrix of tau with respect to C has this block diagonal form, upper block triangular form. And this matrix again is lambda times I sub k. And so now the characteristic polynomial of tau is the same as the characteristic polynomial of its matrix representation, that's C, which is just the product of the two characteristic polynomials, this one and this one. But we can't say that x minus lambda doesn't divide the determinant of R. It might. We have no idea. We don't know much about R. We don't know what the determinant of R looks like. It might have x minus lambda as a factor. And so the algebraic multiplicity of this polynomial might be bigger than k. It's at least as big as k. Well, these two proofs are very similar, so you can take your pick and which one you prefer. Let's talk now about the trace and the determinant as it relates to eigenvalues. We saw in an example in chapter 0 that both the trace and the determinant are similarity invariants. That if A and B are similar, they have the same trace and the same determinant. The fact that they have the same determinant follows from the fact that the determinant of the product is the product of the determinants. The determinant of P inverse is the inverse of the determinant of P. That was pretty straightforward stuff you probably would have learned in the very first course in linear algebra. This one was a little trickier. It used this cyclic property of the trace that we discussed in chapter 0. Unfortunately, however, even taken together, the trace and the determinant do not form a complete similarity invariant. And I'll let you find two matrices, or maybe I already did this, I don't remember, that have the same trace and the same determinant but are not similar. Nonetheless, this does allow us to extend the concept of trace and determinant to a linear operator, finite dimensional linear operator. Okay. I would have avoided some of this missing of finite dimensionality by starting this chapter by saying all vector spaces in this chapter are finite dimensional, and some authors I think do that. But some of this material that we've covered does apply to infinite dimensional vector spaces. The definition of eigenvalue, the definition of eigenspace, the fact that eigenvectors associated with distinct eigenvalues are linearly independent, these do not require finite dimensionality. So I didn't want to do that. And the penalty I'm paying for that is that I was not careful enough in indicating when a result applies only to the finite dimensional case. So I'm fixing that as we go along. I apologize. The notes, the book, if you decide to purchase it from my website, will have these corrections. Okay. So the trace of a linear operator is the trace of any matrix that represents tau. This is the definition of the trace of an operator. Without this fact about the trace being a similarity invariant, this wouldn't make sense. Same thing for the determinant. the determinant of a finite dimensional linear operator is the determinant of any matrix that represents tau. These are well-defined notions because of this result about similarity and variance. However, there is quite a bit we can say about the trace and the determinant as it relates to the eigenvalues of an operator, at least in the case where the characteristic polynomial splits over the base field. And that, of course, will always happen if the base field is algebraically closed, such as the complex field. In matrix terms, let's assume that the characteristic polynomial of a matrix A splits over its base field, and let lambda 1 through lambda n be the eigenvalues of A. That means they're in the base field, counting algebraic multiplicity. So these don't have to all be distinct. There may be double, triple roots, or whatever. Then we can write the characteristic polynomial. First I want to write it this way so I can identify the coefficients. C0 is the constant term, C1 is the linear coefficient, Cn minus 1 is the coefficient of x to the n minus 1. This is a monic polynomial, the characteristic polynomial, so that coefficient's 1. Because the characteristic polynomial splits, it's this product of linear factors where these are the eigenvalues, again, counting multiplicity, algebraic multiplicity. And when you recombine these, the coefficient of x to the n minus 1 is simply the negative of the sum of these lambdas. And the constant term is negative 1 to the n times the product of the lambdas. So if we compare this with this expression here, negative Cn minus 1 is the sum of the eigenvalues. Negative 1 to the n C0 is the product of the eigenvalues. Now, if we set x equals 0 in the characteristic polynomial, Ca of 0 is determinant of negative a, and when you pull a negative sign outside a determinant, you have to raise it to the nth power. N is the size of the matrix, so you get this. Now when you compare this with this, here's C0. Move this negative 1 to the n to the other side, and you see that the product of the eigenvalues is none other than the determinant of the matrix. Or say it the other way, the determinant of A is the product of the eigenvalues. As to the sum, you have to work a little bit harder. What we're looking for is the coefficient of x to the n minus 1 in the characteristic polynomial. So if I write the characteristic polynomial this way, we need to figure out, if we expand this determinant, what the coefficient of x to the n minus 1 looks like. Well, if we expand along the top row, the first term is going to be this entry, x minus a11, times the minor determinant here. But the next term and all the subsequent terms, notice what happens. We're going to have to cross out the first row and say the second column. We're going to lose 2 of these diagonal entries. We didn't lose 2 when we did the first part of the expansion because we crossed out first row and first column. We only lost this entry. But when we go to the other terms in the expansion, we're going to lose 2 of the linear polynomials. So those terms in the expansion cannot contribute to the coefficient of x to the n minus 1. They will have degree at most n minus 2. This is the only term in the expansion that can contribute to the coefficient Cn minus 1. Well, now we do it again. We expand this. The only term that will contribute a coefficient of x to the n minus 2 to go with this x, to get us a contribution to the coefficient of x to the n minus 1, is in the first part of the expansion. So a little bit of reflection will show you that this is the only part of the full expansion that contributes to the coefficient of x to the n minus 1, and that contribution is the negative of the sum of these constant terms. That is the negative of the trace of the matrix. We're adding up the diagonal entries. And so we get this equation, which tells us that the trace of A is the sum of the eigenvalues. So, in summary, for a matrix A, an n by n matrix, if the characteristic polynomial splits over the base field, and if these are the eigenvalues of a counting, I should say, algebraic multiplicity, then the determinant of A is the product of the eigenvalues, the trace of A is the sum of the eigenvalues. Let's take a moment to discuss another topic that won't be used in the sequel, but I think might be interesting for you to see. Suppose we already know that if tau is a linear operator, and if v is an eigenvector associated to an eigenvalue lambda, then tau has a very nice performance on the one-dimensional subspace generated by v. It just stretches v or shrinks v either in the same direction as v or in the opposite direction. So tau is very well behaved on this one-dimensional tau invariant subspace. What if we have two operators? It's reasonable to wonder if there's a single vector v for which the two operators behave optimally. In other words, v would be an eigenvector for both linear operators, something we call a common eigenvector for the two operators. More generally, if we had a family of linear operators, it would be sometimes it is nice to know whether there's a single vector that is a common vector for all of the operators in the family. And that is what this little discussion will be about. First, we need some terminology. So let F be a family of linear operators on V. A subspace W of V is F invariant if it is invariant under all the operators in the family F. The family F is called a commuting family if every pair of operators commutes. So sigma tau equals tau sigma for all sigma and tau in the family. It doesn't look right now that these two definitions are connected. They're certainly different concepts, but the reason they're here is because they are connected. A vector V is a common eigenvector for the family F if for every operator in the family tau V equals lambda sub tau V. For eigenvalues lambda sub tau that can vary with tau. So it's V that we're concentrating on here. It's the same V for every operator, but the lambda, the eigenvalue, may change. So this is a common eigenvector, but it may be associated to different eigenvalues depending on the choice of operator. Then I'm going to leave the following for you to prove as practice. If two linear operators commute, so if there's sigma and tau, sigma tau equals tau sigma, then every eigenspace of sigma, no matter what the eigenvalue is tau invariant. And of course there's a symmetry here, so every eigenspace for tau is sigma invariant. It's just a one or two line proof. The converse of this is false. If you have these two matrices, for example, the only eigenvalue for A is the 0 scalar, and this is its eigenspace. So this is its only eigenspace, and this eigenspace is invariant under the operator B, or the matrix B. So every eigenspace of A is B invariant, but the two matrices don't commute. So this is the converse of this does not hold. Okay? Just because every eigenspace of sigma is tau invariant doesn't mean that the two operators commute. Nevertheless, that result is the key to the issue of common eigenvectors for a family of operators. If F is a commuting family of operators on a non-trivial finite dimensional vector space, we've got a hyphen there, and if the base field is algebraically closed, then the family will have a common eigenvector. We have a commuting family of operators, finite dimensional operators, over an algebraically closed field, such as the complex field. There will be a common eigenvector. And here's the proof. The key is to examine the F invariant subspaces of V. V itself is F invariant. That's trivial. Every operator on V maps V to itself. But since V is finite dimensional, there must be an F invariant subspace, say W, of smallest dimension among all the non-trivial F invariant subspaces. Obviously the trivial subspace has the smallest dimension. We're going to leave that out. So among all the non-trivial F invariant subspaces, there must be one of smallest dimension. So put another way, no non-trivial proper subspace of W is F invariant. Since W is F invariant, we can restrict all of the operators in the family F to W. And I'll denote that this way, family F sub W, or restricted to W. Now, the base field of W, which is the same as the base field of V, is algebraically closed by assumption. So every restricted operator has an eigenvalue. So if sigma is one of these restricted operators from the family, lambda sub sigma is an eigenvalue. There must be one, at least. And therefore, a non-trivial eigenspace. It's a subspace of W. We've restricted all the operators to W. But all the operators in the restricted family, or maybe I should say in the family of restricted operators, all of these operators commute with sigma. So I've taken a particular sigma. All the other operators in this family commute with sigma. They commuted before we did the restriction to W, so they still commute. And so the previous theorem implies that each of the spaces for sigma are invariant under this family. Well, this is non-trivial. It's a subspace of W, because we're talking about the restricted operator here to W, and it's non-trivial. It must be all of W by the way W was chosen. It has no non-trivial proper invariant subspaces. So each of these eigenspaces is W as sigma ranges over the family F restricted to W. So every non-zero vector in W is a common eigenvector for all of the sigmas in this family, all of the operators in this family, and therefore also for all of the operators in the original family F without the restriction of the domains. Okay? So that's the proof.